The new tree we're going to build is this one. Insert KV in proj1 sig of m. To build a new tree, to build a new table, we have to build a new table. What's a table? It's a pair of a tree with its proof of its property. So we have to do exist. And here's the tree we're building. And here's the proof of its property. And to build a proof, we're going to use this lemma that we already proved, which says if you have something that satisfies the search tree property and you do an insert, then that satisfies the search tree property. So this is where we use that lemma in the construction of our interface to an abstract data type. Okay, and then now when we want to prove the GSS theorem, we have to prove that this tree, so let me just simplify this. Simple proj1 sig. We have to prove that this tree, when we look up, we get V. Now, we have to use can relate. Remember in our previous proof of that thing in the other one, we used unrealistically strong can relate, and we can't use that anymore. So we're going to use can relate. And can relate is going to require that that this guy satisfies the search tree property, or in fact, that this guy does. So where's our proof that this tree satisfies the search tree property? If we unfold the table type in T, remember that the table type is a tree with a proof of its property. So we can destruct T. Why can we destruct T? Because T is part of an inductive data type, and it just takes apart the arguments of the constructor. There's nothing special about destruct in this case. And when we destruct it, we get two components. We get A, that's the tree, and HA, that's the proof that the tree has the search tree property. So that's how you use these sig types. They're a pair of a value and a proof that the value satisfies some predicate. And here we're using it to build abstract data type implementations that satisfy the representation invariant. It's useful for many other purposes in the logic. So I will stop here. That's how to do data structures in Coq. That's how to do proofs of properties of data structures. And that's how to package it all together into an abstract data type. And remember what you have to do. You have to define a representation invariant for the well-formed values of your data structure. You have to define an abstraction relation that relates your data structure to the kind of abstract mathematical value that you thought it was supposed to represent. And then you have to prove that each of the operators preserves the abstraction relation in the appropriate way and relates to the abstraction relation in the appropriate way. And finally, you have to prove that any well-formed value does actually abstract to something. So those are things you have to prove. Once you've proved all that, then packaging it together into an abstract data type is easy. As I've shown you in this file, adt.v, there wasn't a single proof by induction. There wasn't a single proof that was more than 5 lines long, because it's just using these representation theorems to show the properties you want.